And thanks for having me here. It's always so good to be back at KITP. So I'll go into some detail about results, but a lot of this talk about sort of halo scale constraints is going to be also a bit of an idea talk, so lots of future ideas. When we look at the cosmic web and it forming in our simulations, I mean, there are really three fundamental things that we can hope to get out of it, right? One is, what's the particle nature or nature of dark matter? What's the nature of the gravity doing the pulling? And what's the cosmology that seeded the input field? And we can then think of these sort of constraints in maybe two different regimes, like Francis Jan said in the summary yesterday, right? So we can think about the large scales, basically the clustering of, say, the galaxies or galaxy clusters. And, you know, that's really cool, but we already know that cold dark matter fits this really, really well, right? So like Francis Jan said, maybe if we get sort of sub% level constraints, there is something there. But for now, it's going to be pretty difficult to really tell what dark matter is from large scales. So then we go to small scales, and I know many of you in this room do that, and so I think that's awesome. But of course, our big problem is always the baryons that happen to live at the centers of these halos, right? And just do all kinds of nasty stuff. And so for these two reasons, in this poll yesterday, I really wanted to scream, what about the intermediate scales, you know? Yeah, it seemed rude, you know. Anyway, nothing against the poll, great poll, right? But I think it's a serious question, right? Is it really only large or small? Is that dichotomy valid, right? And so today I want to talk about the intermediate scales. I want to set up what I mean by that, a bit of theoretical understanding. Then we'll talk about what we're currently doing to measure the structure of halos on those scales. And then I'll go sort of future simulation. So what do I mean by intermediate scales? And we can look at a halo like the one in the title image. Well, what I mean is sort of the regions around the halo where matter is falling in, so it's already non-linear, more or less. Then it encounters the matter that's already orbiting in the halo, and sort of, you know, I would call all of this sort of intermediate regions, everything that's not at the very center, super strongly affected by baryons, loosely formulated. So the question then is, how do we understand it? How can we measure it? So understanding it is something we do in a sort of loosely formed orbiting infalling collaboration, and that term will make sense in a second. What do I mean by that? So I've come to think of density profiles of dark matter halos as really being composed of two different terms that we can, in simulations, pull apart. So in this video, I'm showing you a point for each particle in a simulation for this particular halo. The purple points are falling in for the first time. They have not been in the halo yet. The orange ones have already had a pericenter, and so I'm marking them as these things are orbiting. And then we down here have the density profiles of these two components. And what you're seeing is then when rescaled in decent units, they actually don't evolve much with time. And you can also see that the infalling matter sort of has like a power law profile. The orbiting matter has something that looks like an Einaster profile, and then a really sharp cutoff, basically. It's because these particles can't orbit infinitely far. Right? Now, we can do this for millions of halos, billions of particles, and that has been, I think, quite nice for building a better theoretical understanding of the profiles and especially this intermediate scale region. So here are density profiles, classically not split into orbiting and infalling, for halo samples that have low and high accretion rate at fixed mass. You might say, why accretion rate? Why not mass or something? Well, it turns out that accretion rate really is one number that actually really sets halos apart. You can sort of see it just by eye how different these are, but looking at the slope, d log rho over d log r, makes this even more clear. Right? So what we're seeing is this transition from the orbiting term in here, and then here's this infalling matter, and between them you get some sort of break. Right? A break that we have in the past sometimes called the slush-bag radius, but whatever, I want you to forget about that. Right? We're talking about infalling and orbiting matter here. Now, why is the accretion rate important? Well, it's actually not so hard to understand. Imagine you're a particle, you're falling into a halo, and then nothing happens. Right? The halo just sits there. Well, you're going to go on an orbit, and you're going to stay there forever. Right? But if the halo actually accretes a ton of matter, then your orbit's going to shrink until you stop adding stuff inside of your orbit. So the whole profile basically contracts. And that's what we can see here. We also see it more clearly when we now split into the orbiting only particles. And again, you see this sort of funny profile that steepens a bit and then steepens a lot, right? Like the slope goes to sort of minus infinity, basically. And so what you're seeing is that the fast accreting halos, the orange ones, they have a smaller truncation radius, if that's what you want to call it. Also note that we're down to 10 to the minus 2 in overdensity here, right? So we can measure incredibly small overdensities. This was also really interesting for the infalling profiles. I mean, we had never looked at those before. I think that's a correct statement. And there were also surprises. They go to some sort of constant density. I still don't really understand that. They, again, depend on accretion rate. That makes sense, I guess. So there's a lot more there that we don't have time to really go into today. But the one last thing I'll say about profiles, I guess, is that based on this, I couldn't resist sort of trying to find a new fitting function, right? Because after all, NFW, INASTO, this is what they're trying to model fundamentally, right? They're not going infinitely far out. And so when you plot profiles, so here I have one of these median orbiting terms multiplied by r squared, and you try to fit that with NFW. I mean, it works okay up to a point, but then it really doesn't have this cutoff, right? Same with INASTO, same with a formula we had proposed in 2014. And so here's the new formula which really captures this, and those of you who play with profiles might recognize this as basically a double INASTO profile, right? So you have your normal INASTO term, and then you have a very similar cutoff term where your profile just tanks. Anyway, just wanted to throw that out there. So I think we understand these profiles a lot better now, especially in this orbiting infalling dichotomy. Now, if I asked you, what do profiles depend on? What halo properties? What would you say? It's your first gut reaction. Mass? What else? Ah, very good. Accretion history, yeah, that's right. So they actually don't depend on mass, to first order, right? They also don't depend on redshift. We saw that, right? They actually don't evolve when you rescale them in some reasonable ways. They do depend on accretion rate and halo age. Those two are anti-correlated, but not the same, actually. So they really depend on the whole history, as someone correctly shouted out. They depend on cosmology, on power spectrum slope, right? Importantly. Maybe they depend on the nature of dark matter, right? I think we all in this room want to believe that, right? And it looks like they do, in fact, right? So this is from a paper by Orka Banerjee, where he looked again at the slope of profiles and found that indeed they are different in different SIDM cosmologies. And there's still a lot more work to be done on this. But I think it is fair to say that these intermediate scales especially clearly carry really interesting signatures, right? Of dark matter, of cosmology, of the histories of halos. So given that, we want to measure them, right? So how do we do that? So I think the best place to go to is cluster halos, and I'll explain to you in a second why. But we have to remember that the disadvantage compared to going to very small scales, right, the very centers of halos, is things are going to be big, right? So we might think of a cluster like this, but really, you know, that transition region might be 3 megaparsec for a big cluster, right? So densities are low, everything's hard, right? That's the big downside. How can we do it, though? There are actually many tracers, and this is, again, why clusters are the way to go, I think. So we have the distribution of satellites. Now, you might say that doesn't necessarily follow all matter, and that's correct, but we can maybe certainly tells us something. Weak lensing, obviously awesome, because it tells us something about the total mass. That's kind of ideal. The stellar halo, I'll say more about in a second, of the BCG. And then we have baryonic tracers, so SC, X-rays, right? And this is also important because we need to learn something about the gas and feedback. So they all have their strengths. For example, satellites are, again, taking from Orka's paper, quite differently distributed in some models. And this should not surprise us given what Chanda said yesterday, right? So if dynamical friction and stripping depend on SIDM, then you expect pretty strong effects on the subhalo population, right? So, you know, that by itself could be a really good way to get at SIDM. And I should say that people have already made a ton of progress in measuring profiles out to these intermediate scales. I've put up a few of the faces who have, in my opinion, driven this sort of veritable revolution over the last 8 years or so. So here they're using two different techniques, weak lensing and galaxies in blue. This is for like 1,000 or so DES clusters. And the first thing we should note is that they agree, which blows my mind. You know, and I think it's partly a coincidence. It's simply too good. But anyway, it's awesome, you know. we can again look at more details in the slope, and again we see that the profile sort of steepens, a bit like an NFW, and then you get the sharp break where the orbiting and infalling terms meet here. Right? The black lines are simulations, so they also agree. Perfect. Sounds like we can go home. But again, there's a lot that we don't understand here yet, so I think we should not go home. Instead, we should think hard about how we can do better. And this is something that I'm doing with Alexi Leoto, Song Huang, and a number of other people, like more than could have fit on this slide. And so we want to combine these different techniques minus X-rays. And that's not because we don't like X-rays. It's just because we don't have access to X-ray data, and life is short. You can't do everything at the same time. Right? So now we have an important choice or distinction to make here. As we want to combine different tracers, there are really two fundamentally different ways to do this. Right? We can take power spectra and then sort of cross-correlate, but we ignore information about individual halos where the data came from. Right? That's very powerful in its own way. And people are doing that. But we are going the opposite route, which is we actually want to preserve information about the individual clusters. So we really want to take clusters where we have all of these probes for the same halo. And this has only become possible recently with these overlapping surveys, right? We now have beautiful stellar halo images from HSC. We have DESI, DES, we have ACT for SC, and so on and so forth, right? And these footprints have really started to systematically overlap, where we can imagine doing this for a significant number of clusters. What does doing this then entail? Well, we want to start from the dark matter. So we want to start from dark matter only simulations that could have different cosmologies, dark matter models, you know. And then we want to forward model our observations. So we take the halo properties that we want to know, say mass, accretion rate, ideally the whole density profile. And then we compute somehow the weak lensing signal, satellite distribution, stellar halo, SC profile, and so on. Right? Then we train an emulator to connect these two things and apply it to real clusters, run an MCMC, right, because the emulator is fast, and hope that you can still get some constraint on these things, some useful constraint, while you're marginalizing over all the nuisance parameters in this ginormous forward model that you've built. And so this is obviously a very difficult task, right, to predict these things faithfully enough that you get anything useful out of this. So luckily, we're not completely out in the dark, right? I mean, we can use simulations like illustrious TNG to at least inform our models, right? There we know all the truth of these things. But of course, we have to be really careful, right? Because that's one cosmology, that is one baryonic model. We must be very careful to not take that as truth and to have models that we can really reproduce, say, at least all of the simulations out there to get some sort of confidence that we're capturing what hopefully is reality. So there are many, many components to this, and we're still at the very beginning, so much we still haven't figured out yet. But one thing I wanted to go into a little more detail on is the stellar halos, because I think it's really interesting. So here is a comparison of HSC stellar halos and SDSS for the same clusters. It looks even much better on a laptop screen, but it's really amazing how much more light we're seeing in these new surveys. So Song Huang had an amazing result regarding this. So like he measured the surface density profile in these ellipsoidal shells, and they were connecting it to halo mass, which they could measure using weak lensing. And they found that the tightest connection actually does not occur when you take the whole light. It actually occurs when you cut out the center, right? When you only take the light in some sort of ring. And this makes sense in the context of Azif Attai's talk from this morning, right? So the stellar halo is made of these disrupted satellites. So if you only look at light that comes from these disrupted satellites, you're essentially counting the accretion history of your cluster, right? Getting the subhalos. And that is very tightly correlated with total mass. So we wanted to look at this in more detail in simulations. This, my student Katja Leidig has been leading this. And what they did was they basically took the HSC pipeline and applied it to simulations, right? So we're building these ellipsoidal models, and you're masking out satellites, and you're fitting again, and so on and so forth. And in the end, you come out with sort of a mock-observed stellar halo profile. And these profiles, shown in blue and orange on this plot as a function of radius, match data pretty well. I mean, so it's sort of to a factor of 2. So the black line is the stack of HSC. And then out here, HSC becomes sort of invalid because of background subtraction issues. Now you might say factor of 2, how dare you say that's good agreement? I don't know. I mean, matter of taste, right? But there are 5 orders of magnitude on this plot, right? So I think this is overall pretty impressive, actually. We can now ask the question, how good is any definition of stellar mass then connected to the halo? So for example, we can take the ring between 30 and 350 kiloparsecs against virial mass and ask, what's the scatter in that? And so Katja made this awesome matrix plot. It's a little messy, but we don't have to understand all of it. So here we have inner radius of the ring, outer radius of the ring, and the color map tells us the scatter. So white is good, right? These are tightly correlated with halo mass. And so we see that our conventional ways of measuring that, say, from 0 out to any ring, actually not so good, right? There's much higher scatter than when you take these rings at large radii. Kind of wild. So these are the kinds of things that we're learning, right, as we're trying to connect halo properties and observables. And we'll need many more models like this to build our whole pipeline. But with all of this, I'm really excited about all of this, and I think it's going to be a long-term project, and we'll have to slowly get better at this. But there's always going to be one issue with this forward modeling aspect, right? Like there might be some of you who will say, I just don't buy it, right? You're writing down these models, these formulae, you can never actually capture truth. And I think we all know that really simulations are sort of also what we want eventually, right? And this was pointed out in the SNOWMAS white paper, right, as one of the high priorities, performing simulations with full hydro to get at dark matter physics. Ethan was saying yesterday, right, that currently the simulations are such that we don't always even know where to look, and I think this was well put, right? So the idea is, let's build simulations that at least tell us where to then look, even if we don't believe them maybe in every single detail. So I see sort of a couple of problems there currently, which is that people, and this is, by the way, absolutely no disrespect, to be very clear, right? I think there's a lot of awesome work going on, but what often happens is sort of different groups run different codes and box sizes and resolutions, and in the end you're like, I don't know, right? And then even when we compare, maybe people will take CDM and SIDM, their favorite model. And again, I would do the same thing, right? That's of course what you do. But then how do I know that the effects, the differences they see aren't totally degenerate with some baryonic effect or cosmology or whatever? Right? And so people are starting to get at this now with big suites. Like the DREAMS paper just came out, so they're running, I think, 1,000 simulations of galaxies in different warm dark matter halos, and then running AI on this, for example. Really cool. So we are founding sort of, this is future, this is sort of a very beginning right now, a new collaboration with some people who are in this room to take a sort of slightly different approach. It's actually quite similar to what Julia Dispali was talking about earlier with AIDA, right? But there are some differences, so the idea is to run more like intermediate resolution simulations, fewer of them, but try to keep everything as constant as possible and really compare the different models. And so here is sort of the idea. We don't really have time to go into this slide in detail, but you run some sort of reference simulation with a few boxes, and then you vary your cosmology, your baryons, your SIDM, and we also want to do modified gravity, basically. And so very quick overview. So the good thing is you can cover a large model space, right? And you get reasonable resolution. The bad thing is you cannot test all the parameter combinations. You're not running some sort of Latin hypercube, right? That's what you have to give up. And your resolution, like Julia was saying, is not like TNG. It's still somewhat lower to make this feasible. So far we've just sort of run some fun little test simulations just to sort of highlight, like with totally exaggerated parameters, right? Just to sort of test our repo, get it going, see that you actually get differences. For example, when you run with f of r gravity, you see that these halos are actually in a noticeably different spot, though these models are totally ruled out. So what I really want to one reason I was so excited to be here is to talk to all of you about what models we should run, right? Like what SIDM models, what ethos models, what are we excited about, right? If we have limited computational resources. So for example, we had this discussion earlier about running things that are already excluded. I think we actually come down on Alex's side that we kind of want to focus on things that are not observationally excluded, even if that means you get small effects. But so be it, right? I mean, if they're small, then they're small, and then we've learned something. If they're all degenerate, then they're all degenerate. That sucks, and then we've learned something. Right? So yeah, hopefully it won't all be degenerate. Now, I can't help but finish this talk on an advertisement slide. So One or two of you told me that they use Colossus, and so I cannot resist telling you that Colossus is now a web calculator. And we don't really have time for a live demo, but I just quickly flash it up for you. So you can just go to colossus.astro.umd.edu. You get your standard, nets, cosmology, calculator numbers, and so on, but you can now add multiple cosmologies. Say you want to compare WMAP 3. So then you get a new column here, and then you can do much more advanced stuff like, I don't know, plot power spectra or something like that. Currently, our server is really slow. So here you see the power spectrum slope of these different models, and any plot is downloadable. So you can download these into text files and actually use them for your science. All right, thank you.